Hey everyone, welcome to today's lecture on functional dependencies. Today we're going to talk more about closures. So last time we talked about how functional dependencies can be used to identify redundancy within their existing schema. And we can prevent update anomalies, insert anomalies, as well as delete anomalies by normalizing the database via functional dependencies. And in this lecture, we'll focus on computing the closure. Hi everyone, welcome to today's lecture of functional dependencies and closures in database theory. So last time we talked about how functional dependencies can be used to identify redundancy in the schema design. In this lecture, we'll focus on computing the closure of the set of functional dependencies, as well as computing the closure of some specific attributes. So first, let's have a recap of the definition. So a functional dependency is a rule that says one set of attributes X determines another set of attributes Y. If two records have the same X value, then they must have the same Y value. So in the student relation, a student ID uniquely determines a student name. And in here, we denote it by student ID functionally determines student name. It's basically saying for any two rows in the table, if they have the same student ID, then they're the same students and they should have the same student name. And functional dependencies are the backbone of understanding data relationships, finding keys, and normalizing databases. We'll talk more about normalization in future lectures. So in this lecture, let's first talk about the closure of a set of functional dependencies denoted by F plus or F closure. So this is the set of all functional dependencies that can be derived from the original set using these Armstrong axioms. So we talked about these axioms in last lecture. So basically, these are the tools with which we can generate more functional dependencies based on existing ones. So and we also have more rules that can be derived based on these basic rules. We got union, decomposition, and pseudo transitivity. And how do we actually compute the closure? So this is the algorithm to compute the closure of a set of attributes. So basically, you need to start with the original set of functional dependencies, and then we need to repeatedly apply the Armstrong's axioms to these functional dependencies so that we can get new functional dependencies. So we keep repeating this process until you just cannot add more functional dependencies. So this algorithm is pretty straightforward. However, in practice, as you can imagine, this can be pretty slow because when we have the number of functional dependencies to be very big, this algorithm will be very slow. So that is why we often focus on specific dependencies using something called attribute closure instead of considering the closure of all functional dependencies. So why do we even care about the closure of these functional dependencies? So we care about it mainly for the two reasons. So first, it can help us check whether two sets of functional dependencies are equivalent. So we do this by ensuring each functional dependency in one set can be derived from another set. And secondly, which is a lot more widely considered case, secondly, it lets us infer whether a specific FD, like X determines Y, can be implied by the given set of functional dependencies. So these are crucial for designing databases, normalization, and even optimizing queries. So let's look at an example here. So this is an example of three functional dependencies in F and two functional dependencies in G. So some people might be asking, okay, I want to understand whether these two sets of functional dependencies are equivalent. So to check, we need to verify if every FD in F can be inferred by those in G, and vice versa. So for A determines B and B determines C, they are already in G, so we don't have to consider them anymore. So we only need to consider whether A determines C is implied by G. So the reverse check is trivial because all of the functional dependencies in G are already contained in F. So basically, we need to check whether A determines C can be inferred by those in G. Well, we can just get A determines C based on simple transitivity. So we can see that A determines B, B determines C, and by transitivity, let me see, by the transitivity of functional dependencies, we know that A determines C. So in this case, we can just arrive at a conclusion that F and G are actually equivalent. And here's another problem. So given the relation R with attributes A, B, C, D, E, and we got functional dependencies A, B determines C, C determines D, D, E determines B. So we want to know, sometimes we want to know whether a specific functional dependency can be inferred by these original set of functional dependencies. So here we're asking, is FD, if the FD A determines D implied by these functional dependencies? So to do this, we need to there are two ways we can do this. We can either compute the closure of F, and then we can just check whether A determines D is within F, or we can do something like an attribute closure. So we can compute all of the attributes that can be functionally determined by A, and then we can just check whether D is in that set. So this would be a lot easier than computing the closure of the whole F, because the closure of the whole F includes a lot of functional dependencies. So in here, we don't have to do that. We just need to compute the closure of A, because A is on the left-hand side of this functional dependency that we're trying to check. So basically, we need to compute the closure of A, and then we need to check whether D is in the closure of A. And to do that, we need to start with A, which is the given attribute, and then we need to iteratively add the attributes that can be functionally determined by A. So first we got A, and then we see that AB determines C is not going to help because B is not determined by A, and C determines D is not helping, and DE determines B is not helping with the closure of A either. So basically, what we have found out is that the closure of A is just itself. So bad news, D is not in A. D is not in the closure of A. So the conclusion is that the functional dependency A determines D cannot be implied by F. So this is the way of testing functional dependency based on the original set of functional dependencies. So instead of computing the closure of the whole thing, we can compute the closure of the left-hand side of the functional dependency that we're trying to test. So this is the formal definition of attribute closure. So the attribute closure is the set of all attributes that X functionally determines under a set of functional dependencies. So this is the algorithm to compute it. We start with the original left-hand side. We start with the X, and then we repeatedly check each functional dependency in F, and then we include the new attributes that can be functionally determined by F into the closure of X. And then we repeat until no more attributes can be added to the closure of X. So this is a powerful tool for testing if whether a given FD holds based on testing if a functional dependency holds given a set of functional dependencies, like we have done in the last slide. And also it is useful for testing whether it is a superkey or a candidate key, because basically when you say X is a superkey, you're saying that X can functionally determine every other attribute in the relation, which means that the closure of X should contain every attribute, including itself. And for candidate key is basically saying that, okay, you need to be a superkey and also you need to be minimal. So being minimal means that removing any part of you, removing any attribute from the superkey will change the fact that it is a superkey. So that is what it means to be a minimal. So a minimal superkey is equivalent to a candidate key. So now let's compute some closure of attributes. So here we're going to compute the closure of A based on the given functional dependencies. So we start by looking at A determines BC. So we just put B and C into the set, and then we see that we notice that B determines D. So we can pick D up and it becomes A, B, C, D. And then if we have A, B, C, D, we know that we have C, D, which means that we can pick up E as well, because C, D determines E. So we can pick up E. And then what else we got? E determines A. Well, A is already in there, so we got A, B, C, D, E. So basically, the closure of A contains all attributes of R, which means that A is a superkey for the relation. And because A is just a single attribute, we know that it is by default minimal. So A is also a candidate key in this case. Here's another example of computing the attribute closure. So we got the relation R, and we got a set of functional dependencies. A determines B, B determines C, C determines D, D determines A. So it almost looks like it's circular. So everything is determining the letter after it. So A, B, B, C, C, D, D, A. So it's like everything is functionally determining the letter that appears after it. So if we start with B, we notice that B determines C. So we got BC, and then C determines D, so we pick up D. And then because D determines A, we can also pick up A. So at this point, we have picked up every attribute in the relation. So for the same reason, the closure of B contains all attributes, which means that B is a superkey of the original relation R. And because B is a single attribute superkey, it is automatically a candidate key. And now we can consider a slightly more complex case where we need to check whether the combination of A, B is a superkey. So what are the steps that should be done? If you want to check whether a combination of attributes is a superkey, we need to compute the closure of these attributes. And then we need to see whether the closure includes all of the attributes in the original relation R. And in this case, let's just start with AB. And then, so first of all, we put AB in the closure because they functionally determine themselves. And then because AB determines C, we put C in here. C determines D, we put D in here. And then D determines EF, we put EF in here. And F determines A, well, A is already in here, so thank you. We don't have to put A in here again, A, B, C, D, E, F. So we have computed the closure of AB to be all attributes. So which means that by definition, AB is a superkey of the original functional dependency. And here, we're going to look at another example of finding candidate keys. For this relation, A, B, C, D, we are considering two functional dependencies. A determines B and BC determines D. So now we need to find all candidate keys of R. So basically, in theory, we need to consider all combinations, all proper subsets of the relation, check whether it is a superkey, and then we need to check whether it is minimal. So here we can start by computing these attribute closures. So the closure of A is computed to be A and B. So A is not a superkey. The closure of B is just B itself. And the closure of C is C itself. And the closure of AC is ABCD, which includes all attributes of the relation R. So we also need to check whether AC is minimal. So we can see that it is minimal because if we remove C from AC, A itself, the closure is just AB. But if we remove A from AC, the closure of C is just itself. So none of them are candidate keys. So now we can arrive at a conclusion that AC is actually a candidate key for R because it is a minimal superkey. Well, this is just one of the candidate key, and you can find out whether it has more candidate keys in your own time. So here's another example of testing a specific functional dependencies. Now we need to check whether A determines E based on the given functional dependencies. And to do that, what do we need to do? We need to compute the closure of A based on the given set of functional dependencies. And then we need to check whether the right-hand side, which is E, is contained in the closure of A. So we compute the closure of A by including A itself, and then we see that A determines BC. So we put BC in here, and we notice that B determines D. We put D in here, and we see that CD determines E, and we can put E in here as well. Since E is in the closure of A, then we can arrive at a conclusion that A determines E is actually implied by the original set of functional dependencies. And here we're next, we're introducing the concept of minimal cover. So this will be very helpful in later normalization lectures. So computing minimal cover is the first step in third normal form decomposition. So minimum cover is basically a canonical non-redundant representation of F, where every right-hand side of each functional dependency is a single attribute, and no functional dependency can be removed without changing F, without changing the closure, and no attribute can be removed from any left-hand side without changing the closure of F. So basically, what minimum cover is doing is that it is trying to find a very simple representation of functional dependencies such that the closure is unchanged. So we'll talk more about minimal cover when we talk about the third normal form decomposition. So attribute closure, as we can see, that it is very useful in finding keys, and it is very useful for testing functional dependencies. And we'll also talk about its role in normalization as well as query optimization. So let's recap. So functional dependency means that X uniquely determines Y, and the closure of a set of functional dependency includes all of the functional dependencies that can be derived using Armstrong's axioms, so which are sound and complete. However, because computing the closure of F is very time consuming, a lot of times we're just considering the attribute closure, which effectively finds all attributes X determines. So this will help us test the superkeys, finding candidate keys, verify functional dependencies, and later on we'll discuss how to use them to check normal forms. So these concepts are the foundation of relational database design. So basically, functional dependencies define data constraints, the closure capture all of the implied rules, and attribute closure is our go-to tool for testing these constraints effectively. So these are critical for finding keys and normalization. And in the next lectures, we will be talking about how to use the attribute closures to do normalization, like second normal form, third normal form, and Boyce coord normal form. See you next time.